Hello. As activity in the exoplanet community continues to grow, there's naturally an interest in collaborating and comparing results from different models. This talk will cover a long-standing project in the Earth science climate modeling community called the Coupled Model Intercomparison Project, or CMIP, and some of the lessons from that project that can help exoplanet modelers plan their own successful MIPS in the future. I'm going to touch on 4 key considerations that any ExoMIP should include in planning from the outset: context or rationale, experiment design, MIP logistics, and data sharing. But first of all, a little background for those not familiar with CMIP. It's perhaps best known as the effort that contributes to the physical basis for future climate change projections in the IPCC assessment reports. But for 25 years, CMIP has been conducted as an independent project by the World Climate Research Program, or WCRP. Currently, CMIP 6 is in progress, and we can see from the graphic here that the overall project wheel includes certain core experiments in the hub, and then a variety of subprojects in the spokes that are broadly related by various themes. The subprojects and themes here are not at all arbitrary, and that brings me to the first consideration. The WCRP has developed, via community discussion, a set of grand challenges in climate science, which provide the context and rationales for CMIP's overall design. These grand challenges are meant to identify specific barriers in preventing progress needed to advance the state of the art, to enable targeted efforts with the likelihood of significant progress over a term of 5 to 10 years, even if the ultimate success of those efforts is uncertain, to enable the implementation of effective and measurable performance metrics, to guide research that's transformative for the state of knowledge, and last but not least, to offer compelling storylines that capture the interest of media and the public, and I would argue of scientists from other disciplines that would be interested in the results. In the case of CMIP, for example, climate impacts on human society. Now, planetary science and astrobiology don't have an internationally defined set of grand challenges, but there are certainly existing documents that outline research topics of interest for advancing the field, and not surprisingly, there's a lot of overlap between them. And these can help narrow the context and rationale of any exoplanet MIP. An exoplanet MIP should try to make connections with as many of these topics as is plausible. And the reason for that is clear. We are encouraged to be interdisciplinary in our work, and linking the MIP rationale to broad themes of community-wide interest is to our advantage in connecting to our fellow researchers whose focus is more field or observation-based. The second consideration I mentioned is the experiment design. This graphic for CMIP 6 shows some additional details compared to the project wheel I showed earlier. We can start with the experiments in the heavy black circle at the center. These are identified as core experiments that all participating groups would complete, and they are intentionally very simple in design, many of them just single forcing changes. They also serve as benchmarks or controls for model performance and testing of model sensitivity in known scenarios like modern Earth. And this is important, especially for subsequent experiments that differ significantly from modern Earth, for determining whether an odd-looking result is an artifact of how the model works, or whether some new climate process is really afoot. In the orange oval, we can see the names of the many coordinated MIPS that focus on evaluation of specific model components or targeted topics of research interest. These experiments usually require special sets of forcings. And as an example here, we have AirChem-MIP, which is for aerosol chemistry, VolMIP, which looks at volcanic emissions, ISMIP for ice sheet intercomparisons, and so on. Most of these coordinated MIPS are not much more difficult to implement than the core experiments, and participation in these subprojects is more a matter of modeling group interest and availability. That's also true of the experiments highlighted in the green oval, which fall mostly under the umbrella of the Paleoclimate Model Intercomparison Project, or PMIP. However, I think these paleomIPs are more analogous to exoplanet modeling intercomparisons because they are driven by smaller, less formal groups that are working on non-modern Earth topics that require some special considerations. My next comments are based on my experience with the Pliocene Model Intercomparison Project, or PLIOMIP, which looks at a time 3 million years ago in Earth history when atmospheric CO2 was present, similar to present day levels. If an important goal is broadening participation in the MIP, then the experiment design should be structured to have core experiments that are easy to complete. For PLIOMIP, there were just 2 core experiments. One was a pre-industrial Earth control, which was already being done as part of CMIP. And the other was the core Pliocene experiments with PCO2 set to 400 ppm. For the Pliocene experiment, there was an additional option of running with modern Earth geography if a participating group did not have the ability to modify boundary conditions to match Pliocene paleogeography. By providing a low barrier to entry in terms of experiment requirements, MIP contributors were able to use multiple generations of GCMs as well as EMICs to ultimately provide 15 separate sets of data. All groups were required to complete these 2 core experiments. Beyond that, there were 2 additional tiers of runs that extended the exploration outward. Tier 1, which explored varying levels of CO2 in conjunction with Pliocene geography, and Tier 2, which required more complex manipulations of boundary conditions for testing model sensitivity to ice sheet distribution and alternative paleogeography. These latter runs were completed by those groups that had the time and the ability to do so, and as a result, fewer runs were completed, but this did not affect the key objective of the MIP, which was addressed by the core experiments. The additional experiments here just expanded the scope of engagement. In our case, we were able to include modeling groups that used EMICs, or Earth models of intermediate complexity, sometimes called 2.5D models. In the exoplanet community, 1D and EBMs might be best suited for some of the specialized topics, but there is certainly a place to include them in the work. Moving on now to logistics. Again, if broad participation is encouraged, then having a structured approach to achieving project milestones helps to communicate goals and progress. The steps outlined here were followed by PLIOMIP as a small-scale emulation of the CMIP process and would work well for an exoplanet MIP. Important aspects are the community input to the project design, early publication of the MIP protocols so that anyone not able to attend initial planning meetings could also participate and follow along, and agreement on how data should be shared in group and paper writing responsibilities divided. At a minimum, you can expect a MIP like this to run 2 to 3 years, bearing in mind that most people participating are not likely being funded specifically to work on the MIP, so there needs to be some flexibility in identifying an end date. And this 2 to 3 year time frame matches very well actually with the current TIE project that is being discussed at this workshop. Last but not least, data sharing. PLIOMIP and other small MIPs typically place an embargo on any public sharing, at least until the first publications are in press. That's because the PLIOMIP members not only run the simulations, but do the initial analyses for the intercomparison. That is unlike CMIP, where individual experiment results are uploaded to archives as soon as they are complete. And that's because most of the CMIP intercomparison analyses are not done by the modeling groups themselves, but rather outside contributors. Whenever data are shared, it's important to keep in mind that making data available is not the same as making it accessible. And going back to cultivating broad interest in the MIPS outcomes, if the objective is to get non-modelers interested in the model results, it's worth making output available without any requirement for post-processing. So straight netcdf files that can be plotted in a viewer and ASCII text files that can be manipulated in other ways. It's best to consider saving raw model output and post-processing scripts for a material that is going to be shared with other modelers or people who are able to take on advanced programming tasks. Thank you.